The final challenge consists in the autonomous exploration of a defined space using a differential robot known as PuzzleBot. The PuzzleBot is equipped with a camera and an RP LiDAR, which are used to help the robot to travel to specific goals, avoiding obstacles in the way. We implemented the Book 0 and Book 2 algorithms on the PuzzleBot to navigate from one point to another within the map. Due to the robot's position, we use the node transfer LiDAR data to flip the LiDAR measurements. The transfer LiDAR is responsible for publishing the topic-based scan so that the Book 0 and Book 2 can subscribe to it and evade obstacles. We use a Naruko detect node to subscribe to the camera information and detect Naruko markers within the images. If a Naruko marker is detected, the distance and angle to which the PuzzleBot is located are calculated. This data is published for the Kalman filter. The Kalman filter calculates the odometry and receives data from the Naruko detect to correct the robot's position. The updated position is published so that the book knows the current position of the robot. Then the book is responsible for publishing velocities to the PuzzleBot.
To calculate the odometry, the process of depth reckoning is used. The measurements of velocity and rotation of the moving object are utilized to estimate the change in position and rotation as it moves. Through numerical integration, the displacement in each axis, X and Y, is calculated based on the velocity and rotation angle. These displacements are added to the previously estimated position to obtain the current position. However, depth reckoning can be affected by cumulative errors and requires additional techniques to enhance its accuracy. System noise increases the uncertainty of odometry. This causes the robot to get lost and navigation impressively. That's why we use the PuzzleBot's camera to detect Naruko markers on the map. The system knows the position of the Naruko markers, allowing us to perform transformation from the Naruko's reference frame to the camera frame and then to a robot frame to obtain the robot's position relative of the Naruko marker.
Finally, we used a Kalman filter to merge the measurements from depth reckoning and the ones we determined with respect to the Naruko marker. Within the filter, two C vectors are calculated, one from the odometry and another one from the Naruko marker. The corresponding sigma matrix containing the covariances is computed, which allows us to calculate the mu matrix containing the updated position of the robot. The robot is capable of reaching the given points with an average error of 10 centimeters. Initial tests were conducted with individual points and later progressed to a sequence of consecutive points. This sequence of points is lowered into the robot as an array. Using Book 0, the robot follows the obstacles wall until it finds a clear path directly to the target. In the final test, the robot successfully reached all obstacles with an error range from 3 to 17 centimeters. Book 2 draws a line between the robot's origin and the goal, and the robot follows the obstacles wall until it finds a clear path to the goal while remaining within the drawn line. To ensure that the Kalman filter was effectively merging odometry values with information obtained from the Naruko markers, it was necessary to show how the uncertainty ellipse in RBs reduces when the robot detects a marker.
We successfully completed the challenge by reaching the target points while avoiding obstacles. The Book 0 and Book 2 algorithms proved to be effective, as well as the Kalman filter for improving the estimation of the robot's position by merging odometry with the Naruko marker information. We found that the Kalman filter was effective in minimizing the error in position estimation. Although we encountered difficulties in fine-tuning Book 2 especially, we eventually managed to resolve the issue, and the robot was able to reach most of the objectives smoothly.